Hi, my name is Efrain Gatuzz. I am from Venezuela, and I will talk about proving the ISM in X-rays. First, I want to say thank you to the organizers for inviting me to this conference. I myself was a COSPAR workshop almost 10 years ago, and it was a very good experience, and I will say a very important step in my academic career. Here, first, you can see the image of the sky as seen in X-ray. This is the E Rosita image. So you can see the bubbles, the galactic plane, and many sources, most of them corresponding to AGNs. But today we are going to talk about the ISM. So this is the table of contents for this talk. First, I will mention what is the ISM, the methodology that we use to study the ISM, the X-ray high resolution spectroscopy, the atomic data. This is an important point in this talk. X-ray absorption models, the ISM in the Milky Way, the dust component, and a final warning, which is very interesting. The first question is, what is the ISM, the interstellar medium? I like this definition by Bruce Drain in his book Physics of the Interstellar and Intergalactic Medium. The ISM is everything that is between stars and around galaxies. So this definition includes gas, dust, electromagnetic radiation, cosmic rays, and magnetic fields. In this talk, I will focus on gas and dust. Why is the ISM important? That's a good question too. Well, the ISM is a very important ingredient in both the stellar formation and the stellar evolution processes. The ISM is the environment where the stars are formed. And then during the stellar evolution processes, there are many mechanisms that provide new material to the ISM. So the ISM is a dynamic environment in the sense, from the point of view of the chemical and physical properties. Now, the current model that we have for the interstellar medium includes what we call multi-phase. So the ISM has a cold, a warm, and a hot phase. And you can see variations between them. These phases correspond to physical conditions where the system is in thermodynamic equilibrium, at least local thermodynamic equilibrium. For each one of these phases, you will see different components. For example, in the cold phase, you can identify dust, molecules, and neutral gas. And the temperature is one of the physical parameters that regulates the components. So the cold component, we are talking about 10 to 100 kelvins on temperature. For the warm component, you will have also neutral gas, but ionized gas as well. So we are talking about 10 to the 4 Kelvin. So you can see neutral oxygen, but you can see also oxygen 2, which is oxygen with one electron removed from the atom, and oxygen 3, etc., and other elements as well. And the hot gas with temperature of 1 million kelvins can be seen only in X-ray, and you will see there ions such as oxygen 7, oxygen 8, neon 9, etc. The interesting thing about X-rays is that because the F-rays are highly energetic, they interact with all phases of the ISM. So in X-ray, you can study simultaneously the dust, the molecules, and also the neutral and the ionized gas. In particular, there is a method, high-resolution X-ray spectroscopy is the name, and this methodology allows the direct measurement of spectral features as absorption lines and edges that lead to the identification of ionization species, molecules, and solids. So today I will talk about that. How can we use X-ray observations to study the ISM? This is a schematic representation of the methodology that we use. The technique is called X-ray absorption spectroscopy. So you need 4 ingredients to apply this method. You need an X-ray source. You are not interested in the source. So ideally, it will be a continuum without any features. Typical sources include blazars, if you are using extragalactic sources, or low mass X-ray binaries, if you are using galactic sources. This X-ray source acts as a lamp, providing us with photons, and these photons travels in space and they interact with the ISM between the source and the observer. As you know, because of the atmosphere of the Earth prevent the X-ray absorption, we need satellites, X-ray observatories, to observe these X-ray photons. At the end, you will have a high-resolution spectra, and you can see in the spectra absorption lines and absorption features. And if you have a good model, you can identify ions. For example, in this image, we are looking at the oxygen KH region. I will explain that later on. The point is that in this spectra, you can identify oxygen 1, oxygen 2, oxygen 3, oxygen 7, oxygen 8 lines. So you can study in detail the ionization stage and the physical properties of the environment. This is another representation of the method. You can imagine, for example, as when you go to the hospital and you can use an X-ray source, and then you will have an image of the bones inside your hand. In a similar way, you use an X-ray source. In this case, you can use a galaxy or a low mass X-ray binary, and then you will see the interaction of the X-rays with the material between the source and us. In this case, we are interested in the ISM. Now, we need high resolution spectra. That's the type of observation that we use to do this analysis. The main satellites that we use to do X-ray observations right now are Chandra and XMM Newton, and probably you are now familiar with them. And both satellites include instruments that generate high resolution spectra. The instruments are different. In the case of Chandra, we have the high energy transmission grating, and in the case of XM Newton, we have the reflection grating spectrometer. At the end, both instruments kind of complement each other. They are different, and as a rule of thumb, Chandra will have a better spectral resolution, while XM Newton has better effective area, so you can detect fainter sources. But you can use any of them to analyze the ISM in absorption. They provide you with high resolution X-ray spectra. Now let's talk about physics. What happens between the photons and the ISM? Well, the process is X-ray photoabsorption and also X-ray photoionization. Both are the processes that occurs in the environment. Let me explain this in detail. So you have the ISM, you have a certain amount of atoms. As you know, as you know, the atoms contains electrons. The electrons distribute between the atoms different energy levels. And because of the X-ray photons have high energy, they interact with all these electrons. So depending on the energy of the X-ray photon, it is capable of remove one electron even from the innermost energy level, and this electron can be moved to an upper level, or it can be removed from the atom. If you remove the electron from the atom, you will have photoionization. Then there are cases where the electron is not removed, but it's moved to another level. So you will have probabilities for each electron to produce such photoabsorption or photoionization. The probabilities for each one of these interactions for each atom can be computed theoretically. Some of them can be measured also in laboratories. And I am talking now about the photoabsorption cross-sections. And this term is important during this talk. Cross-section, photoabsorption cross-section. They indicate the probability for each one of the interactions. After the electron is moved to an upper level, there are two decay processes. So the one electron needs to fill the hole, and then you can produce an X-ray photon, a second one. This is the X-ray fluorescence, or you can remove another electron, and this is the Auger effect. This is important. ISM absorption, this process affects all X-ray observations because all the X-ray photons travels in space and pass through the ISM. For example, the Milky Way ISM. So even if you are not interested in the ISM, for example, you are studying AGNs, you are studying X-ray binaries, you need to take into account the ISM effects. Let's talk about atomic data. When I say atomic data, I mean during this talk photoabsorption cross-sections. As I said before, this is the probability for each one of the transitions between the in the atom. This is an example of the photoabsorption cross-sections. So in the X axis, we have energy in electron volts, and the y-axis you have photoabsorption cross-sections. Different panels indicate different oxygen ions. So we have oxygen 1, which means neutral oxygen, down to oxygen 6, which is one oxygen atom without 5 electrons. So this is an example of how accurate are the photoabsorption cross-sections. The first studies to compute the probabilities usually include only a simple edge, like the edge of an stair. This is a green line. It's a simple edge, and the energy of the edge indicates where the photoionization occurs for each ion. Then we have adsorption lines, because not only photoionization but also photoadsorption happens in the interaction between X-ray photons and the ISM. And the red lines correspond to the adsorption lines. But as more and more physical processes are included in the calculation of photoadsorption cross-sections, you can see the black curve is very complex. So we know now that the edge is not a simple edge. You have a lot of lines surrounding the edge, and you should be able to see these lines, of course, depending on the resolution of your instrument and the effective area as well. So this plot is important because it shows you how complex is the ISM absorption. Now let's talk about a good example of how can we study the X-ray absorption. This is the spectrum of a low mass X-ray binary. This is the name of the source. And this is data from XM Newton. Orange and black points correspond to the RGS data. And the red line is the model. So in this work in 2010, they modeled the ISM using only a cold gas model. And they identify many features associated with the cold gas. So for example, magnesium, KH, neon, iron, oxygen, and also this adsorption line. But bottom panel shows you the residual of the fit, and they identify regions where the fit is not good. And they conclude that the fit is not good because their model didn't include dust, and also the model didn't include warm and hot gas. some years later, they perform a better modeling of the ISM by including the different phases. As I mentioned before, in X-ray, you can see simultaneously the dust, but also molecules, neutral gas, warm phase, and hot phase. So here you can see around the oxygen KH region, many of the lines that they identify: oxygen 1, oxygen 2, 3, oxygen 4, 5, 7, oxygen 8. So this is a nice example of what you can do when modeling the ISM. Now, let's go back to talk about atomic data again, because this is very important. In 2013, we analyzed a low mass X-ray humanity, and we identify multiple adsorption lines. So this is a plot of the photoabsorption cross-sections, a function of the wavelength. The vertical lines correspond to the absorption lines that we see in using Chandra data. The solid lines, you can see red, green, and blue, are the photoabsorption cross-sections. These are theoretical. Most of the photoabsorption cross-sections can be obtained only theoretical by doing quantum mechanics analysis, etc. For some ions or some species, you can obtain experimental measurements. In this case, the black line is the experimental measurement for oxygen 1. You can see that the vertical lines are not in the positions of the solid lines. This is expected because these are theoretical calculations. So we are using Chandra as a template, and in this work, we decide to move our lines in order to agree with the observations, because as I say, we have theoretical measurements and we have observations. So we think that the observations are the correct one. So we have done this benchmarking of the atomic data for oxygen. But curiously, you can see that the black line, which is from an experiment here in the Earth, there is a shift to. And we conclude that also the experimental measurements need to be moved. And we say in this work, Chandra has the correct positions. Of course, this is a strong conclusion, and I remember some emails back of the days about this. But keep in mind this result, because I will mention this later on. We conclude that Chandra, a comparison between Chandra, theoretical calculations, and experimental observations, give us the conclusion that Chandra was the correct one. So in the last years, we have done this kind of work. This is important because you have theoretical calculation of photosocial cross-sections, and now you have observations, and you can use them to do a benchmarking. For example, using observation of X-ray novas, we analyzed the carbon absorption in the ISM, and we also did a benchmarking of the atomic data. You can see here the dotted line. This is carbon K alpha. And you can see how the observation helped us to improve our atomic data, because in all the cases, we found that this line was shifted. And then we correct the line using Chandra as template. This is carbon. We did a similar analysis for silicon. For silicon, we use also Chandra observations. And this work is interesting because in this model, we are including only gas, and we obtain a very good model, a very good fit. Now, we know that the ISM also contains dust, especially in the silicon edge. So our work points out that with the current resolution and with the current instruments, we are already in the limit of what we can do in order to differentiate between dust and gas, for example. And then for nitrogen, we have done the same work. Using X-ray observations, we perform a benchmarking of the photosocial cross-section for all the ions, in the case of nitrogen and also in the case of silicon, we identify the cold, warm, and hot phases of the ISM. And in the case of nitrogen, we have measurements of neutral nitrogen column densities, and they are in good agreement with observations from ultraviolet, which is good. Now, all this is important because, again, depending on the model, you will have a different result when studying the X-ray absorption in the ISM. And I just want to point out that we have done a lot of work in the benchmarking of the TOMI data to build the best models that we can have. And now let's talk about these models. Let's go directly to the practical part of my talk, X-ray absorption models. So this is a table of the common absorption models that you can use in ExtrPhy. So in ExtrPhy, you will have WAPs, PH-apps, TBAPs, and ISM apps absorption models. They are already included in the latest version of the ExtrPhy. We also have these two models, IAM apps and INQ. I will talk about them later, but they are available and you can download them, install them, and use them within ExtrPhy. These are the reference, and these are the parameters. NH is the hydrogen column density. This is a measure of the amount of hydrogen in between the observer and a source. This is a very important parameter. You will see that most of the models include this as a parameter of the model. Then you have redshift, because you can have also absorption in the source if you are using an extragalactic source. And depending on the model, you will have the abundances of different elements or the column densities. First thing that I want to say, never use the first two models. Never. Why? Because they use very old atomic data, and then you will have wrong results. So it is important. Please don't use WAPs or pH models. Even if you are not using high resolution spectra, for example, maybe you are analyzing AGNs or X-ray clusters, and you are using EPIC PN observation from Chandra, for XMM, or ACIS from Chandra, it is important. Please never use these models. And if an advisor says that you should use this, you should use one of these models, please tell him or her that no, these models are not good. And if they have problem, you can write me an email and I can explain in details. But this is important. Please don't use these models. Now let's talk about the other models. As I say, the first two are already included in ExtrPhy. Now, this is a schematic representation, as I say before, of what we do when studying X-ray absorption. You have a source, X-ray source, for example, star, galaxy, low mass X-ray binary. You have the flux as function of energy, and then you have the ISM. And when the X-ray photons pass through the ISM, the shape of the spectra change, and you will see the absorption and in the final spectrum. This process can be explained in this with this mathematical equation. You have the observed flux, the spectra that you get in the instrument, from the instrument. It is equal to the spectra or the continuum of the source times this factor, exponential of minus sigma times hydrogen column density. And this is a parameter that is included in the model, NH. What is sigma ISM? Sigma ISM is the sum of the contribution from gas molecules and grains to the cross-section. Here you will have a more detailed explanation for each one. For the gas, you will have the sum over all elements. You have from carbon to iron, and you have the abundance of the element, the fraction or the ionization stage, because you can have oxygen 1, but you can have also oxygen 2, oxygen 3, etc. This factor here is the depletion factor, which indicates how much of the gas is in dust. And then you have the photosocial cross-section, as the one that I showed you before. For molecules, you have similar. You have the abundance of hydrogen, for example, times the cross-section. For grains, it's more complex because you have the distribution of the grains. You need a geometry for the grains, if there are spheres, what kind of shape they have. You also need the size of the grains, etc. And then you resolve this equation and then you obtain the sigma. Now, the only model from all of them that includes grain is the TB grain model. Let's talk about TBAPS and ISM maps. TBAPS is the most commonly used model for X-ray absorption. TBAPS includes only gas component. You don't have in TBAPS grain or molecules. And this is the equation, as I showed before, that TBAPS solve. So you have abundance, ionization, depletion, cross-section. But TBAPS only include neutral gas. TBAPS only include neutral gas. The ISM maps and IEM maps model solve this equation in a different way. Instead of using abundances and ion fractions, we compute directly the column densities for each ion. So you have the column density for oxygen 1, oxygen 2, oxygen 3. What's the difference? Well, ISM maps includes not only neutral gas, but also single and double ionized species. So in ISM maps, for oxygen, for example, you will have oxygen 1, 2, and 3. For neon, you will have neon 1, 2, and 3, etc. IEM maps is similar, but includes highly ionized species. So in IEM maps, you will have oxygen 6, 7, and 8. If you combine both models, you can model the cold, warm, and hot phases of the ISM. With TBAPS, you only have the cold component. This is important, especially if you are using high resolution spectra. You want to model the multi-phase ISM, you need to use something like this, ISM maps plus IEM maps. This is a comparison between ISM maps and TB new. So for the neon region, for example, you have the blue line correspond to TB new, while the red line correspond to ISM maps. It is clear that ISM maps is better because it includes more lines, basically. You have the neutral component, but you also have, in this case, neon 2 and neon 3, and these lines are there in the spectra. The same for oxygen here in the bottom panel. You will see oxygen 1, which is included in both models, but you can see also oxygen 2 and oxygen 3. Here you can see this big absorption line, which is not well modeled. And in the neon region 2, there is a big absorption line here. This is because these lines correspond to hot phases, which are not in ISM maps. Here we are talking about neon 9, and here we are talking about oxygen 7 absorption lines. Again, if you are using high resolution spectra, you will see more than neutral gas. And I recommend you to use more complex model like ISM maps or IEM maps. Now let's talk about the last model here, INEQ, which comes from ionization equilibrium model. This model is different because the parameter is the temperature. One of the parameters is the temperature. Why? Well, because as I mentioned before, you have, for this equation, for the gas, you have the abundance and you have the ion fraction for each element and for each species. For example, you have the amount of oxygen 2 and the amount of oxygen 3. How can you compute the ion fraction? Well, basically you use this equation and you need to compute the population levels in the environment, in the gas. And to do the calculation of the population levels, you need to solve this equation. This is the ionization equilibrium equation. It's equal to 0 because there are not changes in time. Otherwise, you will have here a term basically the variation with time, it is 0. And what this equation says basically is all the processes that ionize the atoms are equal to all the processes that recombine the atoms. So you have ionization equilibrium. This model, IonQ, includes several processes for this creation and destruction rates. The model includes photoionization, Auger ionization, direct collisional ionization, radiative recombination, and dielectronic recombination. So all the models are there. And as I say, this model is more complex because it computes this every time that you do a fit within ExtrPhy. But it is good because the free parameter is the temperature. With this model, we did a fit of multiple galactic and extragalactic sources, and we compute the abundance, column densities, and temperatures of the multi-phase ISM. This is the reference, and we model each component, and we found these temperatures for each component, and each component contains different absorption lines. So this is about the models. In conclusion, if you are modeling the X-ray absorption, especially if you are using high resolution spectroscopy, you should use models that include not only the cold phase but also warm and hot gas. This most of the models are already included in ExtrPhy, but for the last two, including this IonQ, this is the website. You can visit this. This is my GitHub website, and there you will find all these models. You can download them, install them, and use them in ExtrPhy. If you have problems or something, doubts, please contact me, and we can work together on the installation of the models. Okay, let's talk a little bit more about the ISM in the Milky Way. So as I say, you can, using these X-ray absorption models, you will measure the hydrogen column density, the abundance, the temperature of the gas. So we did this analysis for the Milky Way, in which we use a sample of galactic sources. You can see they're here in blue, and a sample of extragalactic sources. You can see them in red. This is the number, 18 galactic, 42 extragalactic, and this is the number of observations that we use from Chandra and XM Newton. For galactic sources, we use low mass X-ray binaries, and for extragalactic sources, we use blazars. Why these sources? Because as I say, we are not interested in the sources, but in the X-ray fluxes. So ideally, these sources should be a continuum. What happens? Well, if you study this distribution of sources, at the end you will measure column densities for the different components of the ISM in the Milky Way. You can measure the galactic halo, and you can also measure the galactic disk, including the thick and thin disk. To create this sample, we just select bright sources with a certain number of counts in the region of oxygen, and no other constraints were taken into account. So because some works, for example, only include sources for which oxygen 7 is present. We prefer to study bright sources because we want to study the distribution of the column densities along the Milky Way. So you have these sources, you apply the model, the X-ray absorption model. We use the last one that I showed you before, IonQ, and then you can measure the column densities. And this is a plot. Upper panel is a plot of the distribution of the column density for neutral, warm, and hot gas as function of the galactic latitude. So you are moving away from the galactic plane. Then you can see here, this is a latitude in absolute values. You can see how the column densities variate from the galactic plane to the largest regions, and it is clear that the neutral and warm distribution change. Even the hot, you can see this kind of changing in the distribution. But in the case of the galactic longitude, it is not as clear as for the galactic latitude, the distribution of the column densities. So with this, you can compute theoretical distribution of the gas in the Milky Way. And this is important because for the neutral component, you have measurement like 21 centimeter measurements, radio measurements. But for the warm and hot gas, you can only use X-rays. So this kind of distribution, how the hot gas distributes in the Milky Way, is an important information that we can provide to the community. And for example, people who do simulation for galaxies need this kind of input in their models, how the hot gas distributes in the galaxies. What else can you do? Well, we did this preliminary study using X-ray sources in combination with Gaia. Gaia is a mission that provides you with the positions, astrometric positions of millions of stars. So if you have the position and you have the X-ray absorption, you can create a 3D map of how the gas distributes in the galaxy. This can be done only in X-ray. Why? Because if you use, for example, 21 centimeter measurements, one problem that you have is that the 21 centimeter measures the column density along the entire galaxy. And also the 21 centimeter only includes atomic gas. In X-ray, you are modeling also molecules, for example. So these are some histograms with the distribution of the sources, the distance that we have. And here you can see the column density is a function of the distance. This is the first Gaia data release, so it's not as accurate as the latest one. And we are now working with the tier that Gaia data release in combination with eROSITA observations, which provide you with millions of X-ray spectra. But this is a preliminary analysis, an example of what you can do to study the ISM. And these are the distribution of column densities, hydrogen column densities as function of different distances. For the first Gaia data release, we are talking about the local ISM up to 600 parsecs. And then if you have, as I say, if you have a hydrogen column density and you have the distance to the source from Gaia, you will obtain a 3D map where you can see the distribution of hydrogen in the galaxy as seen in X-ray. So this is a type of work that you can do. As I say, now we are working with eROSITA in combination with Gaia tier data release. And also we are using spectra from XM Newton and Chandra catalog to do this kind of analysis with a sample much larger. Another interesting thing that we can do now, because we have done a lot of work in the benchmarking of the atomic data, is that now we can identify when the gas is from the ISM and when the gas is from the X-ray source that you are analyzing. For example, in this work, we study this low mass X-ray binary, and we model we have different models for the continuum because there are variations on the accretion state for the binary. But here the important thing is that we model the ISM with the multi-phase model. We include a cold, warm, and hot gas, and then we include a photoionized absorber. This component here is from the binary, it's not from the ISM. And we were able to distinguish hot gas from two sources. So we identify the ISM and we identify the gas that is associated to the low mass X-ray binary. And they are different. And this is a nice work because this is an example of what you can do now, because we have a very good model of the ISM. Now we can do this kind of analysis. But it is important to model the ISM before going forward and looking for other kind of environments and absorbers. The dust component. Well, I am not an expert on the dust component, but I want to mention it because in the last years, a lot of work have been done related with the dust component. Why? Well, because there is a large campaign of laboratory measurements where you can obtain photoabsorption cross-sections for different particles and grains. And then you include the photoabsorption cross-sections in your model. These are some reference, and for more details, please check it out, this reference. They are doing a nice work in including dust component for magnesium, for silicon, and they model the X-ray absorption there. More reference on this work, very recent ones. So for example, for the oxygen, you can see oxygen 1, 2, 3, 4, 5, 6, and 7, and the models now include also the dust. And it has been shown that depending on the source, depending on the statistics, for some cases, you can identify dust absorption as well gas. So these models are becoming more and more complex. In fact, in many cases, when you feed the spectra only with gas, you will obtain a very good fit. That means, as I said before, that we are now in the limit of what we can do with the current instruments. But still, a lot of work can be done right now, including models with dust as well as gas. Now, we are reaching the end of the talk, and I want to give you a warning. And this is a nice example of the importance of the ISM absorption. But to do this warning, I need to move away from the Milky Way and the ISM and the local ISM and talk a little bit about other stuff. And I mean the warm-hot intergalactic medium. What is the warm-hot intergalactic medium? Well, the warm-hot intergalactic medium is gas located within galaxies, which only can be seen in X-ray because of the temperature. And this is important. Why? Because there is a problem, an astrophysical problem known as the missing baryon problems, which says that when you count the amount of matter in the local universe, I mean redshift 0, and then you compare with the amount of matter at large redshift, there is a difference there. So this is the missing baryon problems. And it has been proposed that these missing baryons are located in the warm-hot intergalactic medium. How can you study the warm-hot intergalactic medium? You can do it in emission and also in absorption. And in absorption, this is the methodology. Very similar to the study of the ISM. You have an X-ray source, an extragalactic source. You have your telescope, and you will measure absorption. You should find the absorption at redshift 0, which corresponds to the Milky Way. And this is what we study when we study the ISM. But depending on the location of the source, you should be able to identify absorption at large redshift associated to the warm-hot intergalactic medium. So a lot of work has been done in this regard. But then I want to mention a very important conclusion about this. So there are about the wind. The detection of the wind has been claimed in many works, especially the detection of an oxygen 7K alpha line at this redshift. So it was concluded that yes, we measured the absorption of the X-ray from the wind. But Nicastro, 2016, he showed that this absorption line is not from the wind. This absorption line is local from the Milky Way, and it's not oxygen 7, but oxygen 2. And here you have the spectra. You can see the reference, how he fit the absorption lines, etc. So let's think about this, because the conclusions are quite different. In one hand, we're talking about wind, warm-hot intergalactic medium, missing baryon problems. On the other hand, we are talking about Milky Way, warm gas. The message is clear. The ISM is important. Before studying other components, other environments, you need to be careful about the ISM modeling, especially if you're using high resolution spectra. And the last thing that I want to mention is related with one of my first slides. As I say, in our analysis of oxygen, when we did a benchmarking of the atomic data, we concluded that the laboratory measurements were wrong. And we need to move everything. So at the end, this is a comparison between observations, X-ray observations, Chandra in this case, laboratory measurements, and theoretical calculations. And we conclude in this case that Chandra was the correct one. Well, a couple of years ago, new laboratory measurements were done, and they conclude that indeed Chandra was right. So at the end, what happened with the previous laboratory measurement? Well, they have a problem with the energy calibration scale. So in this example, Chandra won. So this is a nice example of this kind of studies that you can do. The question is, what atomic data are you using? Because depending on the atomic data, you will find this kind of solutions, right? So, main conclusions. ISM absorption affects all X-ray spectra and needs to be modeled carefully, especially if you are working with high resolution spectra. And as I said before, even if you are not interested in the ISM, because you are studying clusters, AEMs, binaries, be careful with the ISM. X-ray absorption provides constraints for the neutral, warm, and hot components of the ISM. And now we have very good models to model all of them. And accurate atomic data is crucial in order to avoid misidentification of the spectral features observed, as in the example of the 100 galactic medium that I showed. So the question is, what atomic data are you using? What model are you using? It is important to know that. The gas component needs to be accurately modeled, and this is very important for dust analysis. Before including dust in your models, you need to be sure that the gas is well modeled. And as one of the results that we have recently is that now, because of the models, because of the atomic data that we have, we can distinguish between the ISM and absorption intrinsic to the source. So this opens a new wave of doing analysis of, for example, accretion states, X-ray binaries, etc. And that's it. Thank you very much. And that's it.